I know I've asked myself that many times, having as a commissioning engineer or design engineer. Sorry, as commissioning engineer or energy auditor, energy engineer. Lots of times you go into a building, so just left scratching your head. So I want to cover design engineers' priorities, some rules of thumb that designers use, steps to load calculations, get into some couple useful equations, talk about load diversity, and talk about boiler chiller plants, how ducts and pipes get sized and routed, and get into a little bit on controls. We could probably have a whole presentation just on the interface and handoff of controls from a designer to a controls contractor. But yeah, we'll touch on it briefly a little bit today and then get into plumbing. So yeah, the engineer's priorities are primarily the budget, and that's the project, the construction budget of the project. Obviously, they have their own fee, but there's the project schedule, and as I kind of hinted at just a moment ago, is design engineers are inherently very, very risk averse, and that kind of manifests in adherence to code as sort of the highest thing. They want to make sure systems are never, ever, ever undersized, and they want to avoid as many scope misses. That is, also something to be avoided at all costs. And yeah, okay, you got to be able to build it too, constructability. And then probably lower, once you've got to check those boxes, then you can get into, well, it's buildable. Does it work? Okay, hopefully. And once you've put enough thought and energy into all of those, then you start thinking about energy efficiency, perhaps operability and maintenance. Those are not going to hear much of that today because it's not very high on most engineers' considerations or priorities. But I love this cartoon that when I saw it early in my design career and stuck with me. So get into some rules of thumb. Cooling loads are often measured in square feet per ton, and more square feet per ton is a smaller load. So it's a little bit backwards, but 500 square feet per ton is not uncommon. 350 square feet per ton is that's a pretty high load. That might be something you see at a operating room in Miami or in the Caribbean or something, where there's a lot of load, a lot of air turnover required. And I think the U.S. average is probably in the 400 to 450 kind of range, and I have seen loads as low as maybe 700 square feet per ton, but that's in maybe Aspen, Colorado, where it's doesn't get all that hot and it's definitely not humid. So a bit of range there, but that's a starting point. And on the heating side, heating loads, this is loads as low as maybe 10 degrees. 10 BTUs per hour per square foot. I've seen that kind of load in Massachusetts in a building that was very, very well constructed, very well insulated, very tight envelope, and 10 BTUs per square foot is also maybe on par for Tampa. If you have a code minimum levels of insulation and that sort of thing, new construction. So it depends a lot really on how the building is built, can have a very strong influence on how big the loads are, and obviously how big the loads are dictates how big the equipment has to be. We'll also mention safety factors. Cooling safety factors could be a 10% to a 25% safety factor, and if you're certainly seeing them compound pretty quickly, where you add 10% safety factor onto maybe the flow of a pump, and then you add 10% safety factor onto the head of a pump, the pressure side of a pump, and those get multiplied together. Then all of a sudden you have a pump that's 21% larger than it ever had to be. Heating, again, more conservative because freezing pipes and bursting pipes is far worse than people sweating a tad. So those are a little higher. And then on the plumbing side, yeah, standard domestic cold water temps in the 40 to 50 range. Maybe you don't get quite that cold in Florida or some other parts of the country, but that's pretty standard for a lot of places. And domestic hot water storage temp in the 120 to 140 range. There's certainly concerns about Legionella, a bacteria that grows in warm storage tanks that are particularly exposed to oxygen. But above 140, that's killed off. So, yeah, any domestic hot water storage tank, only about 70% of its volume is considered usable. After that, it tends to be too diluted, and the temperature, you don't end up getting all that water isn't warm anymore. And building water pressures 50 to 80 psi is pretty good. 80, I think, code requires that you have a pressure reducing valve if your building is above 80 psi. So, yeah, some places, I think in Florida, even you're lucky to have maybe 30 or 35 psi. Water pressure from the street. So places that have maybe a little more terrain and can build a water tower on a hill, will have better water pressure than flatter locales. So, we'll talk about load calculations.
James, can I ask a question?
Sure.
Going back to the previous slide, the like the cooling rule of thumb, was that for a chilled water system, is that like the chiller tonnage and looking at the whole square footage of the facility, it's sort of a coil, like the chilled water coil for an air handler coil capacity?
Yeah, so that gets into sort of what we call diversity. We're going to talk about that in a bit. And yeah, whether you size equipment based, how you size equipment for an individual space versus for, something that serves multiple spaces versus something that serves maybe multiple air handlers and, a whole multitude, a plethora of spaces. So I think we're going to touch on that in a little bit.
Cool. Yeah. I'll sit tight.
Aaron, so you've got your hand raised.
Yeah, I just had a couple questions in the chat. So one was going back to the designer's priorities. Does equipment availability and lead times shift the designer's priorities at all these days?
It will change the ideal sequence of design, and I'm thinking of Hillsborough in particular. It may shuffle some things, and they'll have to get, whether it's a Hillsborough, referendum year 5 or year 6 renovation, or it could still very well be new construction. But getting large equipment ordered earlier probably accelerate some of the, we'll talk about, block load and plant load calculations, and getting that greenlighting getting that settled. It may not be final and have every thing dialed in as well as they'd like it to be, but in the interest of trying to get that large stuff ordered to accommodate those long lead times, it would shuffle some things a little bit in terms of the sequence. When usually that stuff would all be bid together as part of the construction package, but yeah, you need to get that out the door 6 months earlier or a year earlier. That'll just happen far earlier in the process.
Okay, and another question on these rules of thumb. Do something like a variable refrigerant system that lets you have some ability to resize specific areas without remodeling the entire system, does that change anything, or does that alter any, whether rules of thumb or design priorities or anything like that? I guess maybe a question for another slide, but it popped into my head here.
Yeah, I think VRF as a technology can potentially offer some flexibility to, if you had, I don't know, perhaps, 10 tons of cooling and you had, 20 half-ton indoor units, you could have some flexibility as to where all of those, actually get installed within the space. But if you know that the block, the load is going to be, 10 tons, then you could proceed with that, and maybe their locations be sorted out at a later time. And VAVs are maybe similar, but probably don't have quite as same level of flexibility as a VRF system does, just because ductwork is harder to move than copper pipes. Does that answer your
Okay.
question? It doesn't change the sizing necessarily, but it
Okay.
offers more flexibility.
Okay. All right. Thank you.
All right. Sorry, the chat is kind of partly covered up on my screen, so feel free to just come off mute and ask a question if I haven't seen it. So considerations for load calculations are going to be, first and foremost, the outside air conditioned. And this equation maybe looks more involved than it is, but you've got the Q dot is the rate of energy or rate of heat being either put into a space or taken removed from a space. Dot just means it's over time. And so the U is, well, just go to the next one. So that really looks like BTUs per hour. And the U is 1 over your R values. So if you have a well-insulated building, usually you think of, high R values of, well-insulated walls or roofs or whatever. So it's the reciprocal of that. So big R gives you a small U. You multiply that. The A is the square footage of the building envelope, the roof, the walls, windows, all that stuff. And the delta T is going to be your temperature difference between indoors and outdoors. The Q dot is determined that by multiplying all these things together. You can do it for, usually you're using computer programs to do this, but it could, in theory, be done on a spreadsheet if you had, the R value of, the wall assembly.
I asked the question too early before you
sorry.
showed the whole equation. That was my bad.
Okay, yeah, no problem. So, okay, that's this here is great, but what does that actually mean? I just happen to pick Omaha. We've got a few Cox buildings in Omaha, so this might be a decent candidate. There are tables like this, and this is just the top half of a page, but tables like this for 10,000 locations across the across the world. I think 2,500 of them are in the U.S. There's a whole lot of them. Is the point? Each one has a unique identifier here. A lot of them are airports, because weather stations are, airports already need to know the weather, so why not just record it? But this gives you the sort of the annual extreme temperatures, and well, how extreme. You're not going to go for record conditions because that's just too difficult to design for. But what you are going to look at is, on the heating side, look for maybe 99% of the time on an average year, 99% of the hours of the year, the temperature will be above 4.5 degrees. If you want to go a little more extreme, 99.6% of the time, which is to say 30 hours a year, 8,760 hours in a year. I think I've done that math in my head enough times. It's like 34 hours a year. The temperature will be above 0.4 degrees in Omaha, Nebraska. On the cooling side, you've got similar things where it's 2% threshold, a 1% threshold, or a 0.4% threshold, and you've got the corresponding, say, dry bulb temperatures. Just how hot is it? 2% of the time, the temperature will be above 89 degrees with a average coincident wet bulb, which is a measure of how moist, how humid it is. 73.5. 1% would be 91.3 degrees, and a 0.4. You want a more extreme, more robust design. You go for 0.4, but yeah, there's not an insignificant difference here between almost 95 and 89 degrees, 6 degrees, that's real BTUs, that's real energy that you're going to, that's going to be expended to deliver that comfort and potentially push into the next size chiller or boiler or whatever. So, but given engineers' inherently conservative nature, it's not at all uncommon to see all these things designed for the 0.4, or especially on the heating side, the more conservative 99.6. And again, these exist for thousands of cities across the country. And there's, I think, yeah, if you ever want to see one, it's, and are having difficulty sleeping, we could send one to you. Other consideration, the other half of that delta T equation is the indoor condition. If you're choosing to designing a space to be heated to 68, well, if the occupants like it heated to 74, on those very cold days, you're going to have a problem. So that's, there is a ASHRAE standard for this. ASHRAE is an acronym. If you haven't heard of them before, it's the American Society of Heating, Refrigeration, and Air Conditioning Engineers. Well, actually, that's what it used to stand for. It doesn't stand for anything anymore. That's what it used to stand for. And ASHRAE standard 55 governs thermal comfort. So similarly, how cold do you want to make a space? It's going to have the other part of that. Does somebody else have their hand up? I'm seeing.
Yeah, I have a quick question. So
sure.
When you're looking at the design load of a building, a structure, is there any consideration, or is it worth any consideration to climate change and thinking about like the long-term life of that building? Because it's, the building's only going to last but so long, the equipment's only going to last but so long, and the projections on climate change across that seem pretty small for a facility. And so I'm wondering if that's something where people are talking about that, or if that's something people are considering or even thinking about.
There
to
is.
To piggyback off that, also curious about urban heat island and if that's a consideration, kind of similar wavelength.
So to Aaron's question, yes, I have seen a website where it's sort of projecting design conditions. All of these design conditions are, calculated based on like, a 30-year history of, what have the average temperatures in every location been like over a historical period of 30 years. That doesn't move very quickly. But if you're looking for the building to be designed for, the upcoming 30 years, I have seen websites that are looking to forecast out what design conditions might be for a space for, a 10-year, 15, 25-year time horizon. I've seen that link. I'd have to dig it up. But I know it's out there. Matt, heat island, it is a thing. I personally don't have a lot of experience working in sort of downtown or, large, maybe buildings surrounded by acres of parking lot, kind of thing, like heat island. But it can be accounted for. Oftentimes, I would imagine it's often done rather than an exhaustive calculation method, just with additional safety factors applied to things. Alex, you've kind of raised your hand there.
Yeah, I would say that, so my experience there is that you will find not necessarily urban heat islands just as the like broader kind of regional phenomena, but like rooftop equipment, you'll see very often, especially if there's a dark roof, design engineers will bump up those design temperatures that James showed for the area by 5 or 10 degrees. That's pretty common if you have packaged rooftop equipment to do it. And on the flip side, speaking to climate change, extremes get pushed both ways. You're going to see, we've all probably experienced a bit of the more extreme highs and more extreme lows that have been happening more in recent years. So you will find, especially for critical applications on the low side, you might find people for like say 100% central air system, like a makeup air system at, I I don't know, like an operating room or something like that, they might design to a little bit lower than that 99.6 heating temperature because they want a little bit of it's a different way of applying a safety factor. So instead of just multiplying capacity, you're actually trying to capture temperatures, which will matter for things like refrigerant circuits or matter for things like heating coils or glycol percentages. Not just the capacity matters, but the actual temperature that you're trying to accommodate will matter there.
Thanks, Alex. So the indoor condition is the other side of that delta T. You've got the outside, the indoor temperature. That's there we go. Next component is going to be solar heat gain. That's where most of our heat gain, well, I'd say not most, a lot of our heat gain, especially spaces that have lots of windows, come from. And through the course of the seasons, the sun is higher in the summer, lower in the winter, and so that sun angle will change, depending on where you are, latitude, longitude, and how much it contributes, to south-facing glass, or more often in concert with, warmer afternoon temperatures. But yeah, west-facing spaces tend to have higher heating loads than east-facing spaces because the temperatures are higher in the afternoon, compounding the solar gain. So the next component is a big one we're all familiar with, lighting. There's some old fluorescence there. You could have a proper, heat lamp. It's going to put off obviously more watts, more BTUs that the air conditioning system needs to accommodate and overcome. And something that's way more efficient, like our good friends the LEDs, are going to be a whole lot more efficient still, and reject less heat to the space. So obviously buildings are built for people, and a couple considerations around people are their activity level, as you can see kind of described in this table here. Are you seated, kind of at an office? Are you walking or standing? Are you doing kind of bench work? Are you bowling or lifting weights? Playing basketball? Depending on what you're doing, that's going to determine how much heat each person is contributing to the space. And there's the sensible heat, which is just direct temperature, and then there's what's called latent heat, and that's sort of the moisture that we're breathing or maybe sweating. That's the moisture contribution, and there's an energy that can be quantified in BTUs as well. So activity levels is one part, the number of people in the space is the other part. It's kind of obvious, but it's worth stating. And people density by space. So other internal heat gains. So there are lots of other kinds of things. I'm not going to go itemize all of them, but there's certainly things, like computers, there are equipment, there are motors, there could be appliances, like, I say equipment that's maybe like cooking equipment, etc. And there are tables and tables, or pages and pages, excuse me, of tables just like this one in ASHRAE handbooks, and that are in the sort of the built-in libraries of load calculation software. So the next thing that's sort of related to people, and we're done with internal heat gains or heat gains, but the thing that needs to be accounted for when you're sizing a system is the ventilation rate. And ventilation rate is governed by a different ASHRAE standard, 62.1. And you get to look up this table. This table goes on for several pages of that document, of that standard, where there is it depends on obviously the number of people, their activity level. So unfortunately, I just grabbed a portion of this table that is all 5 CFM per person, but there's some other types of spaces, like a gymnasium or a fitness area that have 10 or 15 CFM per person. There is an occupant density. These are default if it's not defined maybe by the architect or the fire marshal, as to how many people per 1,000 square feet. And then there is based on the different kind of space, there's just how many CFM of outside air do you need for the space? Because carpets off gas and other materials and things, you just need some ventilation, fresh air. So this is how you determine, take all these inputs. Excuse me, there's the area part. Take all these inputs and how big's the space, how many people, what's their activity level, and you come up with a total CFM, cubic feet per minute, of ventilation that needs to be provided for each room. Lastly is infiltration. So this is unintentional, unintended, sort of incidental outside air that's coming in. You can see right through the crack in those two doors. That's infiltration, and it could also happen around, say, drafty windows. So you take sort of best guesses as to how well the building is constructed. This is often measured in some seemingly funny units called air changes per hour. In a really, really tight building might be like 0.1 air changes an hour. It's never zero. And a really, really leaky building can be more than 1 air change an hour, where the entire volume of air in the space is sort of passing through. At least you're getting entirely fresh air, once an hour without anybody trying to do anything. That's far from ideal, but definitely happens. Moving on. Yeah, this equation probably looks more intimidating than it is actually is in real life, but the Q dot is power, again, per BTUs per hour. Other parts of the world probably use more familiar electrical power units of watts or kilowatts, but hey, US, we were once under British rule and imperialism. So V dot is going to be your volumetric flow rate of your fluid. So that's going to be GPM for liquids, CFM if it's air, or just liters per second if you're in other parts of the world. Looking at you, Vic, Jesse. This is the Greek letter rho. That's the density of the fluid. CP here is specific heat, so it's the amount of heat, or how many BTUs does it take to raise the temperature of a pound of the material or the fluid 1 degree Fahrenheit. And that's actually how a BTU is defined. BTU is the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. And just for comparison, like concrete, it takes like 0.2 BTUs to raise 1 pound of concrete 1 degree Fahrenheit, but concrete is way more dense than air or water. So, and again, delta T here is the temperature difference. So for water, here's what this actually looks like in real life: BTUs per hour, GPM, 500 delta T. 500 is a nice even round number. How the heck did that come to be? 500 is water at standard conditions, and standard conditions is atmospheric pressure and 70-ish degrees. It's very convenient that the density of water, the specific heat of water, some time conversion factors and volume conversion factors come out to 499.6. It's rounded to 500 easily enough, close enough certainly. And if you're not using water, Alex kind of hinted at some antifreeze solutions. So if you had perhaps a 50% propylene glycol solution in a boiler system that was operating between 180 and 160 degrees, you'd use the average temperature there, 170, and instead of 500 as that number, you'd use 451. If you had maybe an ice storage facility or a building with an ice storage system, and it had ethylene glycol, this is more like your car antifreeze, at a 30% concentration, that number would be 470. So depends on what antifreeze is being used and its concentration. Getting into the air version of this, pretty straightforward, less intimidating. Yeah, it's BTUs per hour. It was your cubic feet per minute, airflow rate times 1.08, all that stuff, instead of being a nice round 500, still the 1.08 times your delta T. And concentration of air doesn't change that much, but the density of air does change considerably with elevation. So your 1.08 will vary depending on where you are in the country and what the altitude or elevation is. The implications of this. Go ahead.
Do you have any nice handy charts with the that elevation information built in, or formulas where that's built into it?
Yes, I do have spreadsheets and whatever that are available, and the elevation is always posted on that nearest weather station sheet for whatever is the closest weather station. But yes, I have that, and
okay,
I could share that as well if people are interested.
Thanks.
Good question. Thanks for asking. So because you're multiplying these things together, if you have a higher delta T and you have the same load, you've come up with, I don't know, 1 million BTUs. Just for example, if you have to deliver 1 million BTUs of heating or cooling, well, you can do it. If you have a bigger delta T, then you need less GPM. So higher delta T, lower flow, that allows for smaller ducts or pipes. And well, that's cheaper to install, cheaper to buy, cheaper, maybe less labor to install. It also means that you're probably going to be flowing less air or water, so there's less smaller fans, smaller pumps, smaller motors, maybe smaller VFDs, smaller wires to the motors, potentially. So there's not just operational cost savings, but potentially you're downsizing some equipment, which is great. Here's where the other shoe drops on the hydronic side to a point. You end up with larger temperature differences, larger delta T's. You're probably going to require larger coils in your air handler for the water to flow through and to sufficiently heat up or cool down the air. So you're going to have bigger coils, that's larger air handlers. If they're need to be large enough, then you're talking potentially larger mechanical rooms. Architects usually don't like giving up any space in their building to mechanical rooms. So that's a war that would be waged. And in so doing, larger coils are going to have higher pressure drops, which are going to, they're just going to cost more because it's more material in the air handler, but they're going to have higher pressure drops, which is going to be more resistance that the fans or pump has to push through. So there's an increase in fan power, which is more energy consumed. So there's an aspect there. There's a sweet spot in the middle, and optimization of that. I'm frankly not familiar with any software that has sort of totally solved that yet, but there is kind of a middle of the road. People don't like going too far in one direction, but this does kind of, you do bump up against this limit as you try and increase delta T in systems. So we talked a couple questions earlier about load diversity. Make sure we cover this adequately. So this is just some arbitrary stuff I came up with, but we've got a series of, we've got an air handler 1 here with 5 VAVs, air handler 2 with 6, air handler 3 with 4 VAVs, and air handler 4 with 7 VAVs. And here's the cooling load. We can focus more on the cooling load than the heating load, but arbitrary BTU values for each space. So the VAV box, each space needs to be sized at, for enough, say, air to actually cool this space, 20,000 BTUs. So that's almost 2 tons. There's 12,000 BTUs in a ton, so just shy of 2 tons. So just a touch over, right around there. This is more 2.5 tons. So if you add all those up, say, okay, well, that's 128,000 BTUs in the space. You do that for each of these systems. Well, that's well and good, but people aren't in both spaces at the same time. Like either you're in one room or the other room, or this one is accounting for when the sun is shining in the east side of the building, and this one here is accounting for when the sun is shining in the west side of the building. It's not going to shine in both at the same time, but you need to have enough air, enough capacity in this VAV box to handle when the sun's shining in the east versus the west. So what is the worst overall condition for this air handler? That's called the system block load. Well, arbitrary, but it's not 128,000. It's only 115,000 BTUs. So just to put some numbers to this, it's only 90%, and these can vary widely depending on the application, the types of spaces, how diverse the different types of spaces are. So you can see something kind of similar on the heating side. You may notice that the heating has less diversity than cooling, because if the lights are off and nobody's in a space, and that's sort of the case throughout the building, then that's the worst case you can have, and that can be simultaneous. So there's usually less diversity on the heating side than the cooling side. So if we've got two air handlers in, say, this building one, you add up the two block loads, that comes to 299. Well, again, the sun can't shine and all the people can't be in, they can't be in all the spaces at once. And maybe the fire code doesn't allow that either. So you end up with sort of a building level diversity. And comparing that, the service to the building doesn't need to be enough to, and maybe we're talking about sizing chilled water piping, but you don't need enough chilled water in building one to simultaneously deliver full cooling to both air handlers 1 and air handler 2, or the same things down here. And then when we get down to the plant level, you can see that the block load for the chiller plant doesn't need to serve both buildings in aggregate at the same time, because maybe one building is shading the other building, for example. So it's only 91% of the sum of the two different buildings. And so that's really the difference. If you look at adding up each individual VAV and compare that to the actual block load, the block load is only not even 73% of, if you add up every single VAV, or every single zone, I should say. And so that converting that to more useful units, that's the difference between say 44.5 tons here versus 32 tons. And this is smaller scale, but if it was multiply that times 10, 320 tons versus 445 tons. That's real money in the size of the chiller plant that might serve such a system, such an arrangement. Luke, does that answer the question you were asking earlier on that?
Thoroughly. Yeah, thanks.
Okay. Yeah. All right. A couple notes on different types of plant equipment. On the boiler side, traditional boilers are non-condensing. We're not even going to talk about steam, but they require an entering water temperature to stay out of their condensing range above, usually with a bit of safety margin, the entering water temperature is above 140 degrees. And if you had a condensing boiler, in order to capture the efficiency of the condensing boiler, which is to say that you're condensing moisture out of the flue gas, and that happens when the entering water temperature is below the dew point of the flue gas. That dew point is somewhere around 127, 129 degrees, something like that. So if your entering water temperature, as a rule of thumb, is below 130 degrees, you're going to be in the condensing range and start to capture that efficiency. The lower the entering water temperature, the better. One easy, quick way to identify if a boiler is condensing or not, or any gas-fired equipment is condensing or not, is that the flue is either it's plastic. It's either PVC or CPVC, and that's a pretty easy tell. Just something to look for. And if you see that a boiler is condensing, you should also see that it has a condensate neutralizer, because this liquid in the water that condenses out of the flue gas is slightly acidic. Actually, yeah, pure water is actually slightly acidic. Distilled water is as well. And so it runs through a condensate neutralizer, which can often look like just a stick of PVC plastic, and the neutralizing agent is oftentimes like chips or flakes of limestone or any kind of lime, something that's basic, and it'll flow through there, move slowly through that, and then yeah, its pH will get to 7, and you can, just enough dwell time, it'll neutralize and then pass through and can just go down the drain then without harming any metal pipes.
Is there any maintenance that's necessary changing that material out over long periods of time?
Yes, well, it's not even changing it out. That stuff gets absorbed slowly over time. And so, yeah, we were actually just in Detroit last week, saw a neutralizer that they had several boilers or several domestic water heaters that were all piped into this. And the thing was 18 feet off the floor, very difficult to access. And then it ran from the neutralizer into a cast iron pipe. Like, if and when that thing runs out of, and nobody checks or replaces the lime chips in there, then it's going to eat away at that pipe, and it's going to be on like the roof of the boiler operator's office, dripping down there, which terribly inaccessible, really lousy design. Putting it on the wall would have been way better. But
a spitball lifespan of these, like before you have to replenish it?
Well, in that case, there were like 5 domestic water heaters all ganged together into one. More often, I see them like mounted on the floor next to the piece of equipment. If the boiler or whatever is on some kind of pad, it's maybe just off the pad from that piece of equipment. So it should probably be checked annually. And maybe you're only adding a handful every year, but yeah, it's not a high maintenance thing. It's just something to check periodically. But if you have a bunch of pieces of equipment tied into a single condensate neutralizer, then it should definitely be checked more often. It's not a hard and fast rule, I realize, but hard and fast answer. On chillers, want to quickly say, yeah, chillers, if you have a water cooled chiller system, it's just put this on the rules of thumb slide, but cooling towers are often sized to reject 25% more heat than the chiller has, than the chiller is sized for. So if you have, than the chiller's capacity. So if you have a 200-ton chiller, your towers are going to reject essentially 250 tons of heat. That's the heat of the compressor largely, and so that's just something to keep in mind. That's why you often see either larger delta T's or larger, maybe on an equipment schedule, you see either maybe higher flows on the condenser water side than you do on the chilled water side, and that's why. On that higher flows thing, oftentimes, thanks, Vic. Just kind of that BTU times 500 times GPM delta T is for a kind of a rule of thumb. If you see that a system has a certain delta T, then here's got a GPM per ton, and this is a language that design engineers sometimes speak. But you can see certainly the difference between flow rate and how you could definitely save some pump power and some money on piping if you're going with a large delta T system. And in either case, with respect to either system, more extreme temperatures are going to be less efficient. So if you had a boiler that's operating at 210 degrees or a chiller that's making ice at 10 degrees Fahrenheit, those are going to be less efficient than systems that are running at more moderate temperatures, like maybe 120 degree, 120 degrees from a condensing boiler, or 45 or even 50 degrees from a chiller. Chiller doesn't have to work as hard. Boiler doesn't have to work as hard. So, just a couple of notes on sizing. I want to leave Alex a couple minutes here as well. I'll go quickly here. The tool that before internet and computers were so prevalent, and whatever, I still have mine, is a ductilator. Some rules of thumb on sizing ductwork. Your low pressure duct has got a standard what you probably have in your house. It's also what you have in a VAV system from the VAV box out to the diffuser. Your medium pressure duct is going to be what is between the air handler and your VAV box. And these have higher velocities. Sometimes you'll see high velocity systems where maybe it's a lab exhaust. You want to make sure that any particulates stay suspended in the airstream, and so you move the air at a higher speed, higher velocity. These values here are saying this is inches of water column pressure drop per 100 feet of ductwork length, and so lower pressure drop is going to be easier on the fan, but perhaps you end up with really big ductwork. So that's some of the VAVs kind of have kind of a step change. They'll go from a medium pressure duct before the VAV box to lower pressure duct afterwards. Return and exhaust is almost always on the low pressure side of things, perhaps even lower than the supply side. All right, there's the ductilator. And there's something similar. It's worth noting, this is where design engineers spend most of their time, is in routing ductwork and coordinating it with structural elements and ceiling heights. You're arranging branch takeoffs and duct crossings and trying to make sure that it all can fit between the bottom of the structure and whatever the ceiling is, and coordinating all different kinds of things. So you can do the calculations, you can do size the plant based on your block loads, and then this is where 70% of your time actually is spent. Hydronic systems have something similar. It's called a pipe wheel. That's a system sizer. And that one's made by Bell and Gossett. Rules of thumb there. Sorry, that one's made by Bell and Gossett. 4 feet per second is kind of the velocity pipe speed, because you can actually get pipe erosion for pipes up to 2 inches. And then for larger pipes, they're done more on a pressure scale, and that's between 2 and 3, maybe 3.5 feet of head, feet of pressure drop per 100 feet of pipe length. Other thing on sizing is fittings can add a lot of pressure drop to a system. A standard elbow in a duct system can be equivalent to 10 or 50, between maybe 10 and 50 feet of straight duct. And I've been in new construction buildings or just looked above ceilings, but oftentimes you'll see just transition after transition and fittings back to back. And so there's this thing called system effects, which is really just a catch-all term for duct design, particularly at the inlets and outlets of air handlers or fans, and they induce extra pressure drop, and that extra pressure drop is a bigger pressure requirement on the fan to get the correct amount of air where it needs to go, and that means more power. So,
question, James, on
yeah.
How do you figure out where you need things like sound attenuators and duct silencers and things like that?
Valid question. Sorry, one thing I want to highlight here is how terrible this duct connection is. It's going into a fan connection, and there's virtually it's an abrupt connection. There's no sort of transition between the two. But yeah, that's a particularly egregious example here. Matt, to your question, it depends on the system, and oftentimes where equipment is located relative to spaces that have acoustic requirements. So you probably wouldn't want to have an air handler room right next to maybe a band or a chorus room in a school, for example, or a testing facility or something like that. Where so it depends on the proximity of the equipment. Just the volume, literal actual sound volume of the equipment, and what the space requirements are. So it's kind of on a case by case basis.
Is that equipment volume is that known and given by the manufacturer, or sort of how is that determined what it might be?
Yeah, that volume will be given by the manufacturer. I will say that of those different types of ducts, airflow systems, the medium pressure duct is going to be noisier generally. Generally, as a rule, that's going to be louder. So if you have that passing by, a space that is going to require or be more sensitive to sound, then something like a sound attenuator, upstream of it passing by that space would be probably advisable.
And do certain types of fittings have significant effects on the noise?
Yes, like a bullheaded T where you have, air, more so air going into something and then teeing into both directions. Those are particularly noisy. There are things that can be done to help reduce that, like elbow turning vanes in the elbows, or a divider to split if it's not, an even 50-50 split between those two. Yeah, there are things that can be done there. And you could go with a different, arrangement of ductwork fittings to try and avoid having a bullhead T like that.
So one thing I'll add to that, James, real quick, is that
Yeah.
Acoustics are complicated. So this is a vast oversimplification, but when it comes to ductwork systems, pressure loss becomes noise. So if there's something that has more pressure loss, it's going to generate more noise. So that's why fittings, especially high loss fittings like a bullhead T, will generate more noise. That's why medium pressure ductworks, if you saw back on the previous slide, low pressure is 0.08 to 0.15 inches per 100 foot. Medium pressure would be half an inch, 0.75 inches per 100 foot. That's going to generate more noise. That's how that manifests. Is pressure goes away, it makes noise and heat, but noise is what you're going to experience mostly. So there's different kinds of noise too, but that's the one that we're going to probably deal with most directly with HVAC systems.
I know Alex has, there's a whole 2 slides here on controls, but Alex has a couple on plumbing. If we can, you stick with us for maybe five more minutes, Alex, you think?
I definitely can.
Okay. Just could we be done in 5 is my question.
Yeah,
6 minutes.
okay.
People have to drop. Understand. Thank you for sticking with us. Controls. This is an ideal scenario versus what happens in reality. I've got an example that Bob Bailou put together for us. He made a tons of notes here, but a couple things to highlight are just disagreements between, this is the points list, this is the system schematic, this is the sequence of operation narrative, making sure all these things agree. And I'd be happy to send out this PDF to anybody who wants to see it, but this is like a bad one, but it's not unique. And so making sure that there's consistency between all 3 elements is really key. Design engineers are probably more, they'd rather leave something out than have it contradict between the two. That's a design engineer standpoint. In fact, I once had my boss, he was a principal of the firm, told me once that he had the perfect project, and he showed me the set of drawings, and he said, I was like, what made that the perfect project? He's like, it was never built. So the fact that nobody ever got to see what imperfections lied inside that design, I thought showed really well just how conservative and risk averse engineers are. Somebody's got a hand up.
Yeah, that's me. Quick question, and it's a couple slides back. Something that is actually in the design guidelines for the district is oversizing the chilled water system by about 30%, which is probably a little bit more than the norm. But they don't have any redundancy, right? They don't have any redundant systems that can back up if one of the chillers or both chillers go down. I don't know if you want to like that.
Yeah. So yeah, with regard to that, thanks Maria for bringing that up. That's actually, we recommended that in large part because systems capacities degrade over time, and certainly Hillsborough has been notorious for not maybe keeping up as well as they should have with that. And so to make sure that the thing still can deliver its at its initial capacity come the end of its life, you know, that was one of the reasons. And coils get dirty and heat doesn't transfer as well. And yeah, there were a few things we put in there to help mitigate that. Is what we put in perfect? I would land pretty hard on the side of no, but it was a way to try to do it a bit more nuanced than just saying, hey, let's add some percent safety factor and then have that get multiplied by other safety factors that compound real quickly.
Okay.
There are different ways to do it.
Yeah.
Sure. Alex, over to you.
All right, thanks, James. So for anyone that doesn't know me, Alex Gambos, also a recovering design engineer. I spent a lot more time doing plumbing in my previous life, so I'm going to take on some plumbing design engineering stuff here. And all I can say, James, is this feels definitely appropriate because more often than not, plumbing gets left to the end of the job with not enough time to do it right. So we're really making the presentation match reality here on that front. So where I wanted to start, we're going to touch, plumbing systems. Most people will tell you plumbing consists of domestic water, sanitary waste and vent, storm drainage, and that kind of stuff. Sometimes you get fuel gas piping thrown in there, and I'll cover that a little bit at the end as well. But that's kind of a regional thing. Some people call it plumbing, some people call it mechanical. It's a little different everywhere. But we'll start with the water side of things. You've probably seen something along the lines of fixture units when you're talking about water. You may be aware of some things like a Hunter's curve or like code-based sizing guidelines for water systems. So first thing I'll say is, what the heck is a fixture unit? It's not very clear, and it's intended to not be very clear. It is really tough to make one number that represents sort of a relative impact of something like a flush valve toilet versus something like a drinking fountain. They don't really behave the same in terms of the way they draw on the water system. So fixture unit is an attempt to do that. It is a measure of impact on the plumbing system. And that's approximately a function of the peak water flow rate, how much it needs at one time, the total water volume it draws off the system anytime you use it. That would be something like a toilet having a large volume per flush, or small volume per flush, and the probability of use. And that's a really big one because that's really, really hard to know. Some stuff gets used more often than others. When you have the same fixtures in different building types, they get used differently and more frequently or less frequently than others. It's complicated and it's very statistical. So all you really need to know is that fixture units measure the relative impact of a fixture on the water system. Some quick definitions: water supply fixture units, WSFU, that's for the water side. Drainage fixture units, or DFUs, that's for the sanitary waste and vent side. They are not equal at all. They're not equal to each other, and they're not equal to GPM, which is what we might all traditionally think of when we think of water flow, gallons per minute. Drainage fixture units are not used for storm drains. Those are sized differently, and it's not necessarily even used for all water or sanitary pipes. And I'll get into that a little bit more later. James, we can hit it. So how do you get from something as abstract as a water supply fixture unit to how much water you're expecting to flow, the pipe to flow, and use some pipe sizing guidelines? Use Hunter's curve. It essentially works to water systems only. It translates between water supply fixture units and GPM. There's an example on the right. There's two big ones. There's the original and the modified. The original is circa 1940, modified circa 1987. The big thing here is you'll notice they're not straight. In other words, just adding more fixtures to a building doesn't necessarily increase the expected demand on the water system, certainly not proportionally. The bigger you get, the less any one individual fixture is going to add to the expected load on the system, because the statistics just say any one fixture is just so much less likely to be used in the bigger building. That's the big word of the day in the middle there, which is stochasticity, which is just randomness. People use it random. People use plumbing fixtures randomly. The timing is random, the use frequencies are random, all that kind of stuff is random. So this is an attempt to try to capture that statistically. Original Hunter's curve is still used as a basis for a lot of model codes, which you might ask yourself, why it's not been updated since 1940? That's a great question. I don't think anybody really has a good answer to that question. The modified Hunter's curves, you'll see a couple different kinds. Those are done by end use. And that was a study that was done to update them based on, what's a hotel versus what's a multifamily residential versus what's a school versus what's an office building. There's a couple different curves that different building types follow there. You'll find it as kind of the basis for some of the hot water system sizing methods, but they're not super closely correlated. So big point here, they're not adapted to current fixture use. I mean, in 1940, toilets were flushed in 6 and 5 gallons per flush. Now they're 1.6 for a lot of applications, 1.28 here in Colorado is the max you're allowed to do. And because of that, they really often oversize your pipes. So you're required to do a lot of it. Design engineers are required to follow these for code compliance, but pretty much everyone knows you end up with oversized water systems when you use it. So,
or low flow aerators. If you have low flow aerators on sinks as another opportunity.
Absolutely. Showers are big as well. Showers, you know, there's, you know, this part of the plumbing code comes at odds with the other parts of the plumbing code, which limit water use. And these two parts just don't talk together super well. So, just how it is. James, we can go to the next slide. So which brings us to pipe sizing. So now that you know your fixture units, you know what flow you need, how do you size a pipe for it? It's a little different than the HVAC pipe sizing methods that James went over earlier. Real quick, you can typically tolerate higher velocities even in small pipes, and you can typically tolerate larger pressure drops over length because plumbing systems just, for the most part, work at much higher pressures than HVAC systems do. So,
and they're also more intermittent.
They are also a lot more intermittent, with the one exception being hot water recirculation, which behaves a whole heck of a lot more like a hydronic system, which is why you'll see some of those things looking about the same. For those that don't have the mental math, roughly speaking, 1 PSI is about 2 to 2.5 feet of head. So if you see 2 PSI per 100 foot, that's like 4 to 5 feet of head per 100 foot, which is really similar to how you would size a hydronic heating system if you see on the recirc sizing guidelines there. Going back to what I was saying earlier, not all plumbing pipes use Hunter's curves or use water supply fixture units to size. The big ones do. Services, mains, big branches, those are all going to want to take advantage of that sort of built-in randomness and diversity factor that the Hunter's curve and the water supply fixture units afford you. But small branches, it's not going to be very helpful for sizing. For small branches, you pretty much want to just know what the fixture is going to draw and assume, you know, it's going to be the total of that, you know, set of fixtures that are on that branch. A good example would be like a single bathroom unit. You know, there's some diversity between those fixtures, but you know, you don't really want to take too much diversity there because all those fixtures get used kind of together. The recirc pipes are sized a little bit differently. They're sized based on heat loss, so they're relatively low flow. And one big point here I want to say is really 3/4 inches should be the minimum for hot water recirc sizing. You see that not done sometimes, and it almost always causes issues with the system. But the other big point here is plumbing systems are open systems, unlike a lot of hydronic systems. Water leaves the pipes, it leaves the systems. So pressures just work a little bit differently and flows just work a little bit different. On the right example of a sizing chart, we won't get into huge detail here, but this is essentially how stuff gets sized. You use velocity and pipe size at your GPM to figure out what pipe size you need. It's just a fancy graph to help you do it fast.
And this is functionally equivalent, but a very different representation of what that pipe wheel
That's correct.
does.
Yep, absolutely. We can go to the next page. So pipe sizing on the sanitary side of things and the storm drain side of things, it's done entirely with fixture units, and it's a lot more complicated is the short answer. Fixture units, even if you have the same group of fixtures, if it's in a different part of the building connected to a different type of drainage pipe, being vertical, horizontal, bottom floor, upper floors of a building, that'll make for different pipe sizes. Sanitary pipe sizing gets complicated fast. It simplifies down. You usually find, you know, a lot of small to medium sized buildings can do with a 4-inch building drain. You'll see that a lot, but there's a lot of complication. Sanitary vent, also the same thing. Vent is what makes the plumbing system stay sealed. It's really important, and it's probably the most important part of the plumbing system is the venting to make sure that when you're draining stuff down, that those water traps, the P traps you see with almost every fixture, the water stays inside. Because if you don't, sewer gases leak out. Not only does that smell horrible, but they also can displace breathable air into space and cause really bad things to happen. So very important, but also a little complicated. Storm drains, those are a little more straightforward. They're based on rainfall. You can find maps and regional information for rainfall, typical design characteristic. This varies a little bit from place to place, but the baseline is usually how much rain is going to fall in 1 hour in a storm that's only expected to have happen once every 100 years. The slope will have a little bit to do with how you size your pipe, but the GPM is going to be based on that rainfall. Usually storm drains, modern storm drain systems have a primary and a secondary. The secondary is primary, and you can't count any drainage that might happen to the primary when you're sizing the secondary. They are 100% redundant pipes. The only difference, one usually terminates to grade, that's the you see, and one usually stays all underground, which is the primary. You want that terminating above grade for the emergency to know the primary is clogged. That's the idea. So real quick, run through, some ENTS stuff we might be able to see with common plumbing pieces of equipment. With water heaters, ways we can save energy, ways plumbing systems can help us, achieve some of our project goals. Obviously, high efficiency equipment replacements are great. Set point schedule adjustments. You'll be surprised how often people just crank temperatures on water heater tanks if they don't feel like they're getting enough hot water. That could be a big one. Flushing and cleaning the tank is also really big. Heat exchangers and tanks just get caked with stuff as it heats water. Stuff precipitates out, and you get this really nasty sludge inside the heating water tank. So just flushing those out can actually have a decent impact on efficiency and energy use. Wastewater heat recovery is a little more fancy, but it's a pretty good one. We're looking into on a couple potential projects with Cox coming up, and HVAC heat recovery. This would be if you have, say, a water-cooled chiller and you have a big source of heat that you need to go to the cooling towers, you can divert some of that heat to preheat your water or partially heat your hot water instead as a way to recapture some of that instead of just essentially wasting it to the atmosphere. Circ pumps and booster pumps, both pretty similar. VFDs and EC motors, big ones. Circ pumps, you'll be surprised. A lot of them are way missized and they don't operate automatically. They just turn on and leave on all the time. So that's a really good one to check. And then booster pumps will come into play if you have low water pressure, like James has mentioned from Nate's. Those are really good for efficiency measures because they're relatively large pumps usually that work at relatively high pressures with relatively larger motors. And a lot of times you can improve them just by recalibrating or relocating where the pressure sensors that they operate off of are located. Hot water fixtures, this is a pretty straightforward one. If you use less hot water, you have to heat less water. So that's a pretty good efficiency measure. Just flow retrofits on fixtures are pretty meaningful. And then ejector and sump pumps, you'll find those kind of scattered throughout, especially older regions will maybe not have really deep sewers. So you'll get a lot of more ejector and sump pumps. And that those, what we can do there is adjusting level sensors in the tanks to when they turn on and when they turn off, and right sizing the tank so they don't have to run all the time. That can be big ones there. So quick preview of how plumbing systems can have an impact on some of the stuff we look for. And then last but not least, on the next page, fuel gas. This one is big because and we see this a lot. This is natural gas, this is propane. This is how a lot of buildings get heat, either directly or indirectly. Almost always you're having gas-fired boilers, if not gas-fired heaters, forced air heaters directly. The big highlights here, you'll see natural gas and propane is the two big ones. There are technically some other fuel gases, but they're really not very popular. Hydrogen is the only one that's going to probably have a factor in the near future. You do see heating oil as well, but that's not really a gas. It's sort of different system type. One big thing to note, just like air density in the HVAC calculations, gas heat content reduces with altitude. This is a big one. You need a bigger pipe for the same amount of BTUs you get out of your gas at altitude. So that's a really big system design impact. That's what something that design engineers should be taking into account. When it comes to pipe sizing, it's based on flow, specific gravity of the gas, and that's different between different gas mixtures, which will be what the utility tells you, and propane versus natural gas have different specific gravities, but it's based on flow, specific gravity length, and the pressure drop you can allow to make sure you have enough pressure left at the end of the system for the gas appliances to turn on and get gas through the combustion chambers. There's lots of different sizing methods, but some big stuff that matters for us is you have to account for the nameplate inputs on all your appliances with no diversity, which is not so almost completely opposite of the block load thing that James was going about earlier. When you size a gas system, you can't assume any diversity in that system at all. It needs to be able to fire all the gas appliances as much as they would ever need to go at the same time. So bit of a contradiction there between the codes, but that's the way it is. So bunch of different sizing methods. These get kind of wonky and detailed. Just know that longest length is most common and also most conservative, and that the hybrid pressure method is something that you can use when you have, say, pressure regulators on your gas system inside the building. If you have like a high pressure system that turns down to a lower pressure system somewhere inside the building. So that's it for this one. Sorry, that was definitely not 5 minutes. I apologize.
No, all right, we're on our last slide. So just wanted to leave some takeaways. There's obviously a lot of considerations that go into any design. The focus is on design conditions at those kind of extreme temperatures, less so in the day-to-day operation at moderate conditions. Does it have enough capacity to cool when it's super hot, and does it have enough capacity to heat when it's super cold? And so, yeah, the intermediate where we spend 99, what would it be? 99.2% of our the year is where, yeah, we actually live, and that's not the design engineer's main thought. There are some of those considerations that go into a design. Sometimes they're synergistic, like the delta T, up to a point, and in other cases, as Alex hinted at a few, sometimes they're competing. Sometimes the code, is not totally pulling in the same direction or cohesive in its instruction. Sometimes what you do costs you. You do something to improve this, well, it has maybe a negative impact over here. So finding a lot of trying to find the balance, and there's no optimization. I'm not familiar, at least, with any sort of optimization tools that are out there that really, can find the best solution for any particular building over maybe the course of a year. But the majority of designers' time is coordinating the layout. The load calcs are done at the very beginning, unless anything changes, envelope wise or glass or those kind of big considerations that we put out at the outset. They're not changing the location of the building, maybe the orientation, the direction it's facing, just how much sun gets in, but usually that's all pretty set. So they spend the majority of design time is spent on the layout and coordinating how everything's going to fit. Yeah, the boiler plant central plants are usually pretty well done in the first 25% of a project design. You didn't hear a lot about operation, access, service because they're not big priorities, big considerations for design engineer. And to me, this means a lot of job security, because all the buildings that are out there, the overwhelming majority of buildings that are out there are messed up in a couple, if not a lot of ways. So that just screams job security to me, as we could be part of the solutions, the solution set to help improve the built environment. Alex, that's what we had. Anything you wanted to add?
Nothing to add other than if you got questions.
Questions, yeah.
Ask. Go ahead. I've got some extra time I can go now, but also just email Teams if you don't. In case
Before we field questions, if folks want to or have to drop, want to mention next month, or I guess it's later this month, the 28th, we're going to have a presentation from Brad Lilliquist on carbon accounting, carbon reduction technologies and solutions. So look forward to that if you have to drop. Otherwise, Alex and I will stick around for some Q&A. Thank you, everybody. Kyle, did you have a question?
Thank you, guys. This is great.
No, sorry. I
Good refresher.
Stop recording.
There it is.